shit, I should probably join the Zoom call.
Hello, everyone. Can you hear me?
Yeah, I can hear you, Dr. Calix.
All right. Welcome. So today, usually takes me a minute or two to get everyone admitted. Okay, so today we are continuing our discussion, right, of this big idea of how exploits work. So far in the previous 2 weeks, we have done buffer overflow, no, sorry, not buffer, set UID lab and format string vulnerability lab. So those two labs, I believe they are due this Thursday, and I've created the links for them, right? So if you should check, if you haven't done so already, go to Brightspace and take a look there. There should be some links on how to, on where you can submit both labs, which are due Thursday night. So now we've gone over those two topics, which are directly related to the next topic that we're going to cover now, which is really like the main topic of this sequence. And so it's the main, so this is really like the main, it should be a fun topic actually. I think you guys will enjoy it. So the way that I do this lab, buffer overflow, is probably 2 weeks. So it'll be this week and next week. You know, today I will lecture about it. Then we will start the buffer overflow lab on Thursday, and I'll lecture the following week probably, and finishing up the lab in 2 weeks. And so remember that week 1 set UID, week 2 format string, and these 2 weeks of buffer overflow lab complete 3 labs, and they prepare you for a practical exam. Okay, so I'll talk a little bit about the practical exam. And the practical exam is really an exam, it's gonna be, I always did it in the classroom. Well, actually, no, I would do it on, you would work on it in the lab, and then you have a few hours after that to submit. So it's really, it's gonna be the same pretty much, except we'll do the same. When we do the practical exam, it might be on a Tuesday, it just depends on when we're ready for it. So the way that it would work is I'm gonna give you just one problem. It's only one problem, but it's a little bit different from the lab. So it's not gonna be the exact, so that's why understanding is important. I will be with you in that lab session, and you can ask questions. And then after that, after the lab session, I'm still gonna give you a few hours to solve it, but you have to submit it by, let's say, 10 p.m., the usual time. So it's really just, as I said, one buffer overflow related problem. And usually what I'm looking for is that you should get a terminal, but it has to be a root terminal. So what that means is that, as you might imagine, set UID is somehow involved, dealing with memory is somehow involved, and the topic that we're covering this week is involved, obviously. So it's usually, that's why I say it's a completion of this sequence with a practical exam, and that kind of will conclude this with that exam, and then we move on to web security, which is, like securing e-commerce websites and things of that nature. So we would be shifting towards that. But so that's, I want to stress that you will have a written exam, obviously, about this on week 6, but I usually I like doing this practical exam. And some students in the past, they have solved the lab, they have solved this problem literally in the lab, right? So if you finish early, you're done. But I usually like, some students may like to have a little bit more time. So I usually give you from, let's say now, 6 o'clock until 10 p.m. So certainly in about 3 weeks or so, 3 weeks from today, probably, exactly, make sure you schedule that period of time to work on this, okay? Now, like I said, it's not that I'm forcing you to work 6-8 hours straight. You should be able to solve it in an hour and 40 minutes. It's designed for an hour and 40 minutes in the lab. However, to reduce stress, I do give you more time. So from 6 to 10. Does that make sense, guys?
Yeah.
So I just want to make sure you're all clear on that one. That will be an individual lab assignment. So that's why it's really important that in the next 2 weeks that you solve this buffer overflow lab and that you have solved correctly the format string and set UID lab. So if you still have questions about those, make sure you ask the questions. All right, so today I'm going to introduce then the very interesting topic of buffer overflow vulnerability. Still, we're in the C, C++ realm because that's really where we have access to memory, as we need to for these things to happen. As you know, C, C++ is one of the oldest languages. It's like the 60s, and it's still pretty much like the powerhouse for everything. All right, so this chapter, so before I get started, are there any questions? All right, so it seems that there's no questions. Great. So let's begin. So first of all, this chapter or this topic, it's called the, can you guys see my, the whiteboard? Are you looking at that? Are you guys still there?
Yes, I can see it.
Okay, great.
I can see it.
Now, one time I kept giving class and I had left the thing, so it's a little paranoid. So this is the buffer overflow topic. Okay, buffer overflow topic. This aligns really well in your book with chapter 4, I think, of the same name. So the buffer overflow. So I use the Wenliang Du book, Computer and Internet Security. So usually when I make these references, I'm talking about those particular chapters. So I very strongly recommend that you read that chapter. What I'm going to explain this week and next week is based on that. So it should be pretty similar, but definitely reading the book is very helpful. Okay, so chapter 4. Okay, read through it there. And as I said, buffer overflow. We're talking about C, C++, and you need set UID. So definitely read those chapters as well. Set UID, then format string. And then now buffer overflow. So solving a lot of these labs, sometimes if you knew everything, it would take you 20 minutes just to type the commands. That's how easy it is. It's only this command, that command, boom, you're done. But understanding why you're doing it, requires a lot of like theoretical framework about this, right? So you have to understand, and a lot of it has to do with memory. So that's really where a lot of it is, right? Is because everything is about, okay, I'm going to put this value in memory. I'm going to put this address in memory. Where am I in memory? Where's the CPU pointing to? The registers on the CPU. What's the next instruction to perform? And so on. Okay, So this is our sequence that we're following right now. So some of the topics that we will cover in this week and next week as related to buffer overflow include, once again, memory layout. All right, so we're going to talk about memory in particular. You know, if you remember last week, I talked about several segments in memory. What's the name of the segment of memory that uses LIFO?
Stack.
Very good, the stack. And although you could do things in other parts of memory, for our purposes for these labs, we're just going to be focusing on the stack. So that means when we're talking about the stack, we're also talking about functions. So we'll be looking at that. Now, don't worry about writing C code from scratch. You know, this is not a C programming class, so I'm not going to ask you to write code from scratch. And instead, I usually just give you the code for you to compile and run. But there's obviously somewhere in there where you have to understand some aspects for this to work. We will also be using Linux commands, as you know. So we will talk about, you know, the buffer vulnerabilities or the buffer overflow, which we need to define what that is. So buffer overflow vulnerability, we'll talk about that. We will talk about writing shell code. Writing shell code, we'll talk about that. And also we will talk about countermeasures or controls, let's call it, which are the defenses that operating systems put in place to prevent these things. So in fact, you know, this is a race between, you know, security people, you know, at Windows and Mac and Linux, right? That they're always updating the software, improving their operating systems, and then attackers who are looking for vulnerabilities, right? So it's really that game of vulnerabilities versus controls that you have in place, right? And so some of these, we will explore the countermeasures. So initially when we start this lab, we will disable a lot of the countermeasures, right? And we are going to proceed to do the attacks. As you make some attacks successful, we're going to turn back on some of the countermeasures and then try out, you know, other ways of getting around the vulnerabilities and so on. And so we're going to be doing that. So for one example of that is, for instance, in the setuid lab, for you to be successful in reading that file, you needed to use the vulnerable ZSH, right? You needed to use the C shell. However, as we will see, we can actually get around CSH by doing other tricks. And so we will explore that later on, because ultimately, right now, we will be using machine code, which are, you know, the instructions that the CPU processes. And so we can do lots of things with that. Okay. So we've talked about memory layout. We've discussed how whenever we have a function, the function will load data into the stack. And so that's an important assumption that we are specifying. And in particular, the stack, oh, I should redraw. The stack will look like this, but we're going to take a piece of it and we're going to call it a frame. And that frame, we can roughly divide it into 3 sub areas. So every frame, or I should say any function, whenever you call a function, function 1, let's say, it allocates a frame in the stack for it. You have, let's say you have another function, function 2, and so function 2 would allocate another frame in the stack with roughly the same division. So again, it would have 3 roughly subdivisions, okay? And that's for every function, function 1 or function 2. So in these divisions, what you have is you have a place where you can store your arguments. And an argument is if I have function 1, these are the arguments, right? So those are the arguments. And then over here, I have my local variables, right? And so local variables will be stored in that part of the frame. Okay. And then over here, we're just going to call this one metadata. But what it implies is that, for instance, when the program finishes execution, so let's say that I've run through all the code in that function and I'm done, I need to return somewhere, right, to the next instruction, right? And so that means that I need to have an address, for instance, in memory. And so that's the idea with the metadata area, that this is where you have, let's say, the address to the next instruction. And this is for the CPU to you know, look at that code and that address and execute that next instruction. All right, so whenever, you know, whenever the CPU is currently looking at a function, it needs to have a pointer pointing to that frame. Okay. All right, so we need to know that terminology in order for us to understand how to proceed. So I'm going to go pretty slowly with just some examples of these ideas. Just like I said, a lot of background is needed, even though the command, you know, getting one of these vulnerabilities to work, it just takes a few commands, doesn't take any scripting or anything like that. But we do need a little bit of background. For this lab, you will need the ASCII table again, so keep that handy, you know, as you start working through the lab, because you will need it. And then, as I said, we will explore the controls. I have them over here. So one of them is address randomization. You know, canaries, and so on. So we will come back to these ideas later. You will also be using GDB, so hopefully you had a bit of time to play with that in the previous lab. So we will need it again. We will also introduce in this lab the idea of something called a NOP sled. It's a pretty interesting concept, and NOP stands for no-op, and I will come back to it. And then, as I said, shellcode, we will look at what that is. But ultimately, shellcode is, as I said, is the program that you would write in C++, now converted to the machine code, because remember that we're going to be doing code injection. And to inject code in memory, we can't inject it as what we see in C++ in our editor. We have to actually use the converted version of that. So we will talk about that a little bit. Okay, so certainly we will explore these main ideas. And the lab should be a lot of fun. to get the results. All right, so those are the concepts. So that's kind of the brief overview of the problem. So now let's get started with the main ideas, and I will run through them here. So let's start with the stack. All right, so let's start thinking. Remember, the stack is a place in memory. Okay, so we want to take a look at how. Remember, we've said that functions need the stack. That's how they've been designed in an operating system. They've been designed to put their values in the stack. So let's imagine that we have the following functions. We have void function char1, right? And then I have like A1, which is, if you notice, it's like a pointer to characters in memory. So this usually implies that that's an address. And then I'm going to have int A2, and this implies that that's by, whereas the previous one was by ref, this is by value. And then I have int A3. All right, and so those are my arguments. And then over here, I'm going to have a function. So let's use printf, for instance, as an example. So I have printf, and we're just going to say, A1's value is, and then use some kind of a, format string. It doesn't matter what it is. Just an example. And then comma, and then it takes, let's keep it simple, a little bit of pseudocode, so A1. Right, so that's usually what we're doing, right? So we have some arguments that we pass to the function A1 takes that argument, and it performs some task like a print statement there. Okay? So let's, let me actually do this. So now that we have this function, from another function, we're going to call that function. So I'm going to create void main, right? And then I open curly bracket, close curly bracket. And I'm just going to say, if you notice, this is function 1. So I'm going to call function 1. And then in function 1, I'm going to say hello. That's the value that goes to A1. All right, and then 5 and 6 for the two integers A2 and A3. Okay, so far, this is pretty straightforward, is what you would have expected. But it's important to become familiar with these concepts, because this is what you will be doing, right? It's important to understand you have arguments and you have local variables as well. And so you want to be aware that whenever you make this function call here, you go immediately into the stack. And that means you're going to have a frame in the stack where you will store your arguments, your local variables. And also remember that you need to know the next instruction. So here I'm just going to say next instruction. So that means once function returns and it finishes doing its job, the code will come back to that instruction. All right, so you need to have, this will have an associated address. Wherever the code is stored, you're going to have an address that indicates where to go. Okay? So after executing this, you come back to the next instruction. Okay? So looking at this previous example, we would think of this as being the stack in memory, And so therefore in the stack, we need a frame. We allocate it the moment that function is called. This is metadata, right? So for instance, if I'm just going to make up an address, I'm going to say 0xb1ff, for instance, right? And so that address of the next instruction, where I'm going to store it here, like that. You see? So I know the pointer that is holding this frame is saying, okay, when I finish execution, I need to go to 0xbiff. Well, that's that. And so I then come to that instruction over there. Okay? So now over here is where we're gonna store the arguments. So these are the arguments over here, right? So this would be, and notice that it's LIFO. So the way that it's designed, because it's a function, is that you store them in reverse. So for instance, here, this is going to be A3. Remember, A3 is this one. And then this is A2. That's that one. And then this is A1. That's that one. Okay? So you're storing those arguments in that frame in the stack. Now, the local variables, that would be if we had int x or something, right? But we're not going to worry about that for now. We'll see that later. Okay? What's important is that you understand that, okay, it all starts with code. If it's a function, it'll go on the stack. And then I know now that all of these are located in various places. And then you can say like, okay, I have, 0x89. I'm just making up numbers here. 0x90, 0x92. So the stack itself is associated with addresses. Now, you don't necessarily know what those addresses are, but it is associated with addresses, okay? And so it's because it's all memory at the end of the day. So those are addresses. All right, so now let's kind of make this a little bit better. So let's write, the function a little bit more completely. Are there any questions so far?
Good so far.
So far, all right. So now the function, again, character, notice this is an address to another place in memory, but a place for where we're storing a string, not where we're storing, let's say, a CPU next operation or instructions. We have int A2, int A3. Okay, and then I open curly bracket, close curly bracket, right? And now, imagine I have, B1 12, right? So this is a buffer of size 12. Notice that, okay? Because this is important, all right? This is a small space in memory. Only 12 characters or so, buffer 1. I also have int B2, int B3, and these are local variables. And then I can have here A2 equals A3 plus B2 or something like that. Have some operation, okay? But these here are the local variables, and the arguments are in the parentheses. And then, again, we do void main, open curly bracket, close curly bracket, and we make a function call hello. 5, 6, or something like that. So the question is now, how do we store this in memory? And then here, we can call this one next instruction. And again, I'm going to give it 0xbiff. All right, so that's just an address where I have the instruction. It could be another address, obviously. Just using that one. So now we can picture this in the stack. Once we call the function, we just called it. We have the function instance, if you will, a frame. And now in here, right, we're going to store our data. So this is called a return address. And it's going to be 0. The addresses are longer, but just using a shorter representation. Now the arguments are A1, A2, and A3. So I'm going to store those here. A3, A2, A1. And I'm actually just going to make a little room there for the actual values. So given that I have these values, right, I'm going to store them. So I'm going to say 6, 5. What do you think goes here in A1? Given this logic, what would you say goes there?
Anyone? Is it a pointer to the string?
Pointer.
A pointer to the string, right? So let's just call it an address. Very good. It's an address, right? Another address. So think about that, right? So stack has addresses. Notice there's an address for the return address. There's an address for the string. There's actual values in there and so on. Then let's just say this is more metadata. What's important there is that there's specific size, 1 byte, 2 bytes. And then after that, we have the local variables. We still need to store the local variables, right? And so the local variables go in this part of the frame. All right, so we're going to say there that we have B1, right? And then we have just intentionally making B1 a little bit bigger so I have enough room. And I have B2, and then this B3. Okay, so this is the space for the local variables. And now B1 is really the important one here. So what is the size of B1? It has size 12, right? You can see that here. So really the way that you can think of it is, let's say this was allocated in memory, and the way that it's written in memory is like this. It goes from B0 ... to B12. Do you see that, guys? Actually, sorry, B11, right? It should be B11. Do you guys see that?
Yes, we do.
What's one important thing about this? Which way am I writing this variable? So I write something in B1, right? In which direction in the stack am I writing? Am I going up or down?
LIFO, like that first, like 0, 1, 2, 12. So
Yeah, but I just mean, am I going in this direction or that direction as I enter values for B1?
going down.
Well,
Is
think
it
about it. It goes from
going up?
B0 to B12, right? You guys see that?
So you're writing up because I don't know.
Yeah.
Why does it go backwards?
Yeah, exactly. So just look at it this way. So 0, 12.
1. Oh. So you're going up?
It's going up, right? Do you see that?
Okay.
And so it's important because you're writing in that direction towards what? Towards the metadata and towards the arguments. Do you see that? So what's one danger of this, do you think? What's one possible danger of this? If you're just writing, let's say you somehow just have access to the memory directly, you start writing here and you're just writing in that direction. What's one danger of that, do you think? Just intuitively, what would you say?
Well, if you don't specify like what kind of data can you overwrite?
Right, and that's another way of saying that you don't specify that you're going to stop at 12, right? If somehow you're able to just continue writing, right? What could you possibly write here or overwrite here? Let's put it this way. If I'm just writing from here, what are the things that I'm overwriting?
You could overwrite the return address.
Return address, right? And why is that significant? Why is overwriting this? If I could do it, I don't even know if I can, right? But if I could, because I can overwrite, let's just say I'm just going to overwrite everything, right? So I can overwrite the return address. I can overwrite this address. That's another address. I can overwrite the 5. I can overwrite the 6 because somehow, magically, I can start writing into, now we know that B1 could receive a value, right? So it means that value will be assigned to B1. Now, if you write a properly written program, whatever value you enter should be written in that direction, but should end at the allocated space, right, guys?
Correct.
But if unfortunately you're not disciplined, C gives you so much power and control over memory that what could happen? You start overwriting, right? And you overwrite this return address, that, and all the other ones. So let's think about what's going to happen. Let's start at A3. If you overwrite that 6, what could happen to the program? Maybe it's going to crash. It's going to give you bad data, right? The same applies for A2. What happens if you overwrite A1 with something else? What would be the impact of that?
You're going to be like directed to a different address or?
Well, A1, the variable, is basically an address to another place in memory where you're storing hello, right? So if you overwrite that, you won't be able to find that hello anymore, correct? It's gone. Do you guys see that?
Mm-hmm.
But that's about the extent of the damage. So you lost that piece of data. But what about this one here? What if you overwrite that return address, 0xBIF? Where does 0xBIF take you? And what is it exactly?
That function?
Can you be a little bit more, so it's not a function exactly. What is it?
Is it executing that instructions?
It's definitely hex in the sense that it's written in hexadecimal. 0xBIF is hexadecimal, but it is an address, right? It is an address. That's why it's called a return address. What did I say that address was pointing to? It's here, right? 0xBIF. That's why I actually called it BIF, so that you knew it's a bad it's a bad guy from Back to the Future, right? So what is the significance of 0xBIF for the frame? So remember what I said, the CPU has a frame pointer, basically pointing to that frame, executing. When it finishes, when this function finishes execution, the CPU looks at that space in memory and reads whatever is in there. You guys see that? And then the definition is it will execute the code at that address. So 0xbif is the next instruction after the function. So what, it's literally what the CPU will do. The CPU will actually, go in there and say, okay, now I'm going to run this. Do you guys understand that idea? Guys?
Yeah, it makes sense.
Yeah.
All right. Okay, so if you understand this idea, I'll ask the question again. So let's say that I somehow magically can start writing in V1 and I don't stop and I just keep going and I overwrite 0xbif. Let's say I overwrite it with just gibberish. What's going to happen when the function finishes? What will the CPU do? It's going to read that space in memory, right? It's going to find gibberish. What will happen? It'll go to that place in memory. But it's not going to be 0xbif. It's just going to say 0x, F, E, 47, whatever. That points maybe to nothing. Maybe it points to a place in memory that has garbage, or maybe it points to, it's not even an address in space, right? In the memory space. And so, it's actually not even. So what will happen to the program at that point? What will this, if the CPU goes to an address that doesn't exist, tries to read whatever is there, what will happen?
Would it just crash?
It'll crash. It'll crash. What you will get, and this will happen. So what I just described will happen to you a lot when you're doing this lab. It'll be the one thing that, the common theme. The error that you will get is going to look like this. It'll say segmentation fault. You will see that a lot. It just means that you've crashed your program. It's a type of error where the address didn't find anything, and so it crashed. Okay, or it found something, but it's garbage. Either way, it didn't execute correctly. Is that idea clear, guys? Because this is the fundamental thing. I'm literally right now, I'm explaining to you the heart of this whole problem, what you need to achieve. So is this clear? Now, what are things that you know? You know the size of this. You know where this starts. It starts at B1. You know the start. You know the size. And you know that the frame, every frame follows the same format. Local variables, metadata, arguments. Always, right? And you know that a few bytes from that variable, you have the return address. So what's the danger there? So we have already established that we can write garbage there and get a segmentation fault. What else could you write there in that space? What else could you write there?
Can we write a different return address?
A different return address. Very good. An actual valid return address. Do you see that? And that's an entirely different story, because now you're intentionally saying, you know what, don't jump to xbif. Jump to this address, which I figured out, where I have some, and by the way, I have some code there And now I'm going to get, and that code can be anything. So then you can, this is code, you're changing the flow of the code execution just by changing that address. Does that make sense? Guys? And that's really the key of your labs, okay? Every lab, every single one of these 2 labs, you will have to come up with schemes to jump to places in the code via this mechanism of the return address. Okay, so that's really important to understand that that's the goal that you're doing. You will literally have to, get a notebook or something and write down those, your return addresses, because you'll have to figure this out. All right, so are there, yeah, so that's an important one. So I don't hear any questions, so I'm just going to assume it's clear. Okay. Now, another way of thinking about the stack is we can write it like this, and we can think of the stack as a structured area. So let's say this is 4 bytes, this is 4 bytes. Then we have A1, A2, A3, okay? And then down here we have, let's say, B1, B2, B3, right? So we have our variables there. One thing that's important is, one way that you want to think about this is that you have a register in the CPU. Let's say it's called the EBP register. The names don't really matter that much. And then what matters is that you have an offset associated with it. So that is to say, the register is a pointer. And that's usually how it works in C, right? You have, you could be pointing there, or you could be, let's say the frame pointer actually is pointing there, right? So if it's pointing there and you want to access A1, and A1 is 8 bytes or 8 bits, some value they're going to change. So then you would just do EBP plus 8, and that's it, because the way that C works is that it's just going to look at whatever the data type is, bytes or bits or whatever, couple of bytes, and it's going to use that unit. So all you have to do then is increment it by 8, right? And it'll be able to figure out, okay, I want to move this data type 8 times. Okay, and so on. And then this one might be 4 bytes. So then it would be EBP plus 12, right? Because it's always from the position where the pointer is at. So what this shows you is that you can sort of, with this with these ideas, figure out, okay, the address space has structure. I need to figure out what it is. I need to figure out where I am. And then I need to figure out how to sort of move around it. Okay, so definitely addresses are pretty important here, and as I had said before, these are also addresses. Okay, these are addresses. Okay, but the 0xBIF, the return address, what's important is that initially it won't be pointing to the stack. Instead, it'll be pointing to another area in memory outside of the stack. Let's say the text area or some area like that where you would have your code, okay? So to the CPU, an address is an address, but just be aware that this return address would be pointing to another place in memory, just very much like this one was pointing to, say, yet another area in memory where you had hello. Okay, so that's why, C is such a powerful yet kind of dangerous language, is because you have all this flexibility of just changing addresses to move around memory. The this flexibility gives you power and speed at the cost of making mistakes that are more critical. Okay, so the return address is certainly a very, very important issue. All right, so let's do one more example. Now what I'm going to do is I'm going to have a couple of functions, and we're just going to see how these functions interact with the stack, okay? So let's take a look at the function. So let's say function, same one. Right, so we have that function over there. And we have our variables, remember, of size 12. And notice again, I keep pointing to this size, right? So then I have int v2, int v3. But now notice over here I have g. And what is g? G is another function, okay? G is another function. And then over here I have the next instruction. Okay, next instruction, because it's the next instruction after G. Okay, then over here in the main, oops, in the main, I'm going to have a function. I'm calling function, which is that one, right? And I'm going to say hello 5, 6, right? Same function. And then this one also is the next line. Okay, and then I closed curly bracket there. All right, so that's the code as I have it. Oops. That's the code as I have it. Now we want to look at this in the stack. So I will use a different color pen when I start making the connections, but let's just imagine. So we're, we go into main, right? So let's follow, let's do follow the flow here. So main and then function. Can you guys see my pencil when I move it?
Yes.
The actual pencil, do you see it, or just when I write?
No, I can see it.
The pencil? Okay. All right. So that's better because I don't have to. So we see where the pencil is, right? So function hello 5, 6. That's the first place. So you go into that function and immediately in the stack, remember this is the stack. This is the stack. And we're going to create a frame for it. I'm going to create a frame. And that just means that I'm going to allocate some space in the stack for function. Because I'm currently executing this one, right? I'm currently executing that one. So now it follows the structure. I'm going to have a return address. And I'm going to have another address to, let's say this is the calling function. Right, so that's another address. Then I'm going to have my variables A1, A2, and A3. So I have those variables, and I have the other variables in function, which are V1, V2, V3. Probably make this a little bit longer. Okay, so that's the frame. like that, right? So that's the frame for function. Okay, so now this return address, what would it point to? What should, if I'm gonna draw an arrow here, as you can see here, where does it end? Where does that arrow end, do you think? Does it go there? Am I in the right place? Or which way does it go? Where does this return address, where should it point to?
Does it go to next line in void main?
Yes, very good. Excellent. Thank you. Good job. Goes there, right? That's the next instruction. So this is important to understand this flow. Now, the function that called this is main. Right? So you can see that. It points like that. Okay, very good. Actually, like, let's use different colors for the different frames. It's better. All right, so very good. And then we have the variables in there. Now there's only one frame pointer, and the frame pointer is currently, so let's call that frame pointer. Right, and the frame pointer is currently pointing there. Actually, I'm going to switch colors. And it's currently pointing there. That's the frame pointer. Now, you execute the code. So let's go back to red. All right, so you're in the function, you do all of this, boom. Guess what? In the function, you have another function called g, correct? We have g, and we haven't defined g per se, but that indicates that now we need another frame. So if you can see, I'm using another color for another frame. Okay, so I'm going to switch back to red. And now here, this is the frame for G. Make sense, guys? So what does the G have? It'll have the same things. It'll have a return address. It'll have a return address. It'll have the address of the function that called this. So in this case, it would be function, right? The one that called it. Right, and then over here, just generically, I'm going to say G's arguments, since I haven't defined the function G. And then over here, I'm going to say G's what? What would these be? If these are the arguments of G, what are these?
Those the variables?
The local variables. Remember,
Where?
they're called the local variables, okay? So very good. So yeah, so those are the local variables. So hopefully it's starting to make sense to you that there's a specific structure. Things are placed in specific places. That's why computers are very deterministic, right? Very, it's very always kind of the same thing. That's why these exploits always work. It's always, relative in the stack, relative to some pointer, and then they're always in there. So see, if you stole the code, remember that the assumption is you have access to the code, you can read the code and figure out how to create this exploit, and then you target, assuming, of course, that the code initially did have a vulnerability. If there's no vulnerability, there's nothing you can do. But if there's a vulnerability, you're going to definitely exploit it, okay? Right now, I'm just showing you the background to understand how things can be stored in memory, and then we're going to see the vulnerability itself. So now I ask you so I'm going to use another color for G, the orange one or golden, whatever that is. So the return address for G, what should it point to?
I said the function at the top.
But where? What part of it? Remember, it's the return address. That is to say, when G finishes executing, you want to go to that next instruction. So where is that?
We go back to void function.
Which one, sorry?
Would it go up to the void function at the top? Because that's the one that's calling it.
Void function, void function, not there at this time. Where did we call G? Where did we call it?
We usually call it at the void main, like a.
We didn't call it at the, I mean, just look at the
Well,
code.
we would
Where's G in this code?
inside the other function.
Inside function, right? Inside function. And specifically here, right?
Okay.
There. That's where it is. And so if we want to return, once we finish executing G, where would you think you should return? So what should it point to? Guys, where? So it should point to the next instruction, right? So it should point, after G finishes executing, it should point there. Do you see that? Does this make sense? And so this is what's important, because the CPU, as it's looking at this frame, it finishes executing, it's going to look at what's in that return address and then call this next instruction. It's going to call that one. The problem is, what's the problem? If you were able to change this return address to something else, again, think about it. You could then, the CPU is ready to execute a command or instruction, so it just needs an address. Is this clear? Are there any questions? I should ask. Are there any questions? All right, it seems like there's no questions. I think you guys are still there. Maybe you fell asleep. But anyway, so let's now do one last example. All right, so we're going to do an example. You can expect something like this on the exam. I'm just going, it's really about understanding, the memory. So understanding the stack in memory, right? So the way this will work is I'm going to give you some code and the stack, and then you have to tell me, you have to kind of follow the flow. All right, so let's do the example. All right, so we're going to say void function int a int b And then curly bracket int c equal 8. All right. And then I'm going to have an if statement in here. If a less than or equal to 0, return. However, if it's not equal to 0, or yeah, less than or equal to 0, then you do function a minus 1, comma c. And then notice now the next instruction but I'm going to actually give it an address. Let's say 0x2000. Okay? So I've given it an actual address in there. Oops, sorry. 0x2000. Okay? Now when you have, what type of a function is this? When a function calls itself?
It's recursive.
Yep. All right, so it's recursive. So now we have void main, and void main calls function 2, 4. And then notice over here, next instruction is going to be 0x1000. All right, so that's another address in memory where that instruction would be. And we're just imagining that situation, okay? So now the trick is we want to basically kind of imagine this as it would flow in the stack in memory. Okay, so I'm going to draw, make this a little bit bigger. All right, I'm going to draw a stack there. Or actually, you know what? Different color here. I feel like the stack would be yellow somehow. Okay, so let's go back. So the first thing we want to do is, we started void main, right? So we call, you see my pencil there, function 2.4, correct? That's that's where we started the program. So that means we need a frame for 2.4. Okay. So I'm going to try to fit it in there. So what do I need? I need a place for the return address, right? I need a place for the return address. I'm going to have this space, which is just part of the metadata. I'm just trying to fit everything in here. So this is going to be the frame for F24. That instance of the code, remember, so that instance of the code gets called. We plug in the parameters in here for, oh, sorry. I actually need to fit 2 numbers in there. So I'm going to say 4 and 2, right? Those are my 2 values. They're placed in there in memory. Make sense?
Yes.
Now, what's the return address? The return address goes here, right? So return. I'm just going to write return, okay? But it implies return address. What value goes there?
0x1000.
Yes, excellent. 0x1000. That goes in there. Perfect. Good job. And then over here, we still need, do we have any local variables?
and C equals 8.
Mhm.
Very good. See that? That's your local variable. So in the stack, we did this, right? So now we're going to look at executing F24. So that means F24 goes in here, right? You can see my pencil flying. A is 2, B is 4, C is 8. So we go in here. So A is 2. Is 2 less than or equal to 0? No, right? So that means we need to do what? Do a recursive call on the function. You guys see that? So now it's going to be function. So now when we call this function recursively, what do we need to do in the stack? What do you think I need to do in the stack? Because now this became what? This became function A is 2. So 2 minus 1 is what?
1,
1. And C is
8.
8. So this becomes F18, correct? So I just made a call to a new instance of the function recursively. Where does it go and where does it need to be? Where does it need to go? It goes in memory. So if it goes in memory and it goes in the stack, I need to allocate a new frame. Now notice I had before frame pointer. The frame pointer initially was pointing there, right? But because now I'm in this one, the frame pointer is going to point there. You see that? That's the current function that's being executed. Okay? Now, we need to lay out the parameters. So what do I need? I need, how many arguments does it have?
1.
2. It has 2. A and B, right? 1 and 8.
Oh,
And then it's got, what else? What follows after the arguments?
the return address.
The return address and the metadata, right? So I'm just going to say return. And then what else? What's the last thing? The local variable, right? So let's look at the arguments first. 1 and 8, right? So we're going to plug them in here. Those are A and B. The local variable is again C. That's 8. What is the return address for this one?
0x2000.
Yes, very good. 0 because it's the next instruction, right? So 0x2000. Remember, it's recursive, so it's always just going back to the place in code, but with new parameters. So it needs to figure out, based on the logic, which way it goes. All right, excellent, guys. Very good job. Now, let's finish this. Okay, so we, all right. So now we did F18. We have everything in the stack. Now we go back in. F18, C is 8. Is 1 less than or equal to 0? False. Therefore, we call the function yet again. 1 minus 1 is equal to what?
0.
1 minus 1?
0.
0, right? 0. So now I have F0, and C is, we're never doing anything to C, so it's still 8. You see that? We have yet another instance of the frame, or sorry, of the function. We need another frame. Now, frame pointer will point there. Do you see that? Because that's the that's the frame that's currently being executed. So now we specify, again, the same thing. So this is the last time I'm going to do this, but you can see how it works, hopefully, the mechanism. So I have, this time I have, what do I have? I have the parameters 8 and 0, correct, guys? 8
Correct.
and 0. I have the return address here, which is, again, 0x2000, because it's recursive. I have the metadata, and I have my local variable, which is going to be, again, 8. Right, and so now, I once again go into this code. 0 is now, in fact, equal to 0, so I return. And at that point, I finish the execution of the function, and the frame pointer then says, oh, you just finished executing, right? Great. Now I'm gonna use another color for this, yellow, and it says, oh, I'm gonna destroy that. You know, not destroy it, but just forget about it. But I need the frame, the address, sorry, the address where I need to go. Okay, so I look at the address, it's 0x2000. Oh, I know I need to execute that next instruction, whatever it is. Then I finish that and I go back to yet the other frame. So the frame pointer then, the way it would work is, okay, it was pointing there, then it pointed there because it's going back. Then it finished executing that, and it goes back to the next, like that, and so on. Do you see that? Do you see how this works, guys? So we use the combination of these return addresses, right, to know what place to go back to, and then, you know, and then the frame pointer just knows, okay, I'm back at that other place. I need to access the variables of that other place. Are there any questions? Really, no questions? Wow. Okay. But did you guys understand the basic mechanism? You have, you know, the frame pointer just points to the place where the locations are, the address, and then the CPU just needs to know, where do I go once I finish? So I need to know the return address. So the key mechanism is that the CPU, you know, needs to know that return address to know what instruction to execute, these and that. And that's where, because that's going to be code, you know, machine code, basically. That's, as an attacker, that's the thing that you want. You want to change this return address to point to something else. Preferably, if possible, another address in memory that you control. Now, both the lab and the practical exam will require you to do that. You're going to have to figure out two things. You're going to have to figure out, first of all, when you run I'm going to give you a program in both cases, right? And you're going to have to figure out where the address is located. So you have to figure out these positions, okay? That's what you will have to figure out. Where, it doesn't matter which one, as long as you know where it is exactly. The second thing is, you need to figure out not just where you want to write something, but also the what. So it's the where and the what. Okay, so first of all, what places in the stack are return addresses that the CPU is going to eventually get to. And then once I know them, I want to know what to write there. You know, what address to write there, right? Now, the exact position is very important. So let's say that you wrote an address, and symbolically, I'm just writing it like this, right? So that means that you know, part of it started before the actual space that should be the return address. that won't work, right? It cannot be just offset. It has to be exactly in the right place. All right? And so that's really important. All right, so I hope that made sense. And that's just really an example of how, you know, how this works, right? The memory. This was all just memory, just talking about memory. Okay. So the first, as I said, that's why this this takes 2 lectures, because, you know, there's a lot of background. But that was the discussion of stack in memory, as you have seen. That's the discussion of the stack in memory. Now we are ready to move on. So I'm going to give you guys, you know, so if you have any questions, please ask. Otherwise, we're going to move on to the next part of this, which is, you know, the vulnerable program. Okay. All right, so it seems there's no questions. All right, so let's continue then. All right. Actually, let me use this up here. So now we're going to look at the vulnerable program. All right. So of course, for that to happen, we already established that if you have some code with functions in it, it maps to a very specific structure in the stack, which is memory. That's what we established in the previous discussion, right? That, you know, just that. Now the question is, how do we, now given a vulnerable program, how do we exploit that in some way? So let's take a look at that. And actually, this simple code will be the basis of all your problems. If you remember, the very first problem you had in the class this semester is I asked you, what is the vulnerability in this code, right? So I'm going to do that again. Okay, so I'm writing this code. I have char buffer, size 12, say 12 bytes, right? And then int b2, b3. And then I have a string copy. Now there are many functions in C. Some check bounds, boundaries. This one doesn't. String copy, just whatever the input is, grabs it, and it writes it to whatever the output is. Okay, so for instance here, I have buffer, comma, string. And then you can have, you know, dot, 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 whatever code, and then return. All right, so, and then I have void main, open curly bracket, close curly bracket. I have char my string right, and we're just going to say that this is a very dot 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 very long string. All right, so that's a long one. Imagine as long as you want. And then over here, I do function my string, comma, 5, 6, dot, dot, dot. All right. So if you look at this code, what can you tell me about it? Void is, you call main first. You have a string, my string. Then you call function, which is this one over here, right? You call that function. And you pass to it my string, which is, this is a very long, very, very long string. You pass that on. So now you come here to void function. String is now my string. Buffer is 12 characters, can hold 12 letters. Okay, buffer, because it's size 12 bytes, right? It can hold 12 letters. Now B2 and B3. This function here, string copy, literally copies whatever is an S in string into buffer. You see that? It does that copy there. It copies like that. Okay? Now, I ask you the question. So, given everything that I've explained, what might be the problem in this code, do you think? What do you think might be the problem?
Is it that buffer is only supposed to have 12 characters and we have a lot more than 12 characters?
That's right. That's exactly right. Imagine, in fact, great answer. And that is the basis of the entire problem. Okay? Imagine that for whatever reason, this is 512 bytes, right? This one only holds 12 bytes. So I am trying to copying 512 bytes into 12 bytes. You see that that's a problem, right? That's a very big problem. And so when you do this, now very good. Now imagine what's going to happen in the stack, right? So we're going to go back. Now we're going to imagine the stack. I'm going to draw a stack a little bit like that. Okay. I'm going to create the frame and the frame pointer. So frame pointer is pointing there. So I have, the 6, the 5, those, that's the string address, right? So that, that string address is this one. Okay, remember? So this is a very, very, very long string. So somewhere else in memory, you have this is a very, very, dot, 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 very long string. In fact, it is 512 bytes long. Here we have the return address. Then we have, the previous frame pointer, or let's just say more metadata. We don't really need to use that. We just need to know that it's of a specific size. And then now, remember, this is where the local variables are stored. Local variables. So we're going to go back to our program. And this program has these local variables, right? It's got buffer, B2, and B3. You guys see that? Because we're laying out the space and memory for function. And so we need to allocate space for buffer and for B2 and B3. So now, This is going to be buffer. These are the local variables, buffer. And these are going to be B2 and B3. And that's the frame for function. Okay? All right. So that's the frame, right? Now, buffer is of what size? Actually, I'm going to use a different color for this. Blue. So
12.
buffer is of size 12, correct?
Yes.
Right. So that means we define this 0 to 12. Do you see that? Now, string, this one is from 0 to 512. Remember, we defined that. 0 to 512 versus 0 to 12. So if I go back, and now what we're doing is we're copying that 512 into buffer, that space. But the problem, and here's the really important thing, string copy does not care to measure if the size where I'm writing to meets the size of the thing I'm reading. It takes like, imagine it just takes 2 pointers and it just starts reading whatever it finds in one pointer until it finds a null character, and it writes that into the other place in memory, okay? So for instance, what that means is that, you know, this would have, you know, this would have a null, let's say a null character there, right? And so string copy would just read, you know, so it's just gonna read. Okay, I read T, you know, this, oh, that's probably too, let's just say it reads, oops, you know, this is, and so on. You see that it's starting to write in that direction, but it doesn't, it's gonna read all of this until that null. It'll know when to stop there. And so it just keeps writing, and then it writes, and guess what? It writes over this. It writes over the return address. It writes over the string address. It writes over this, and it keeps writing. How much does it write into the stack? How much does it write? How many bytes? What was the size of the original input? Somebody wrote something? 512, very good. Very good, Josh. Exactly, 512. So you wrote 512 bytes into the stack when you were only meant to write 12. Do you see how that might be a problem? Guys, questions? And so this is the heart of the buffer overflow problem, because you now, if you find a vulnerability, you know the structure, you know the CPU eventually will take whatever address is in there, and it's going to jump to that area in memory and run that code. So this tells you, first of all, find a vulnerability. You already know what the vulnerability looks like. It looks like this. That's why this slide is called a vulnerable program. So the vulnerable program is that vulnerability there, right? That's the first thing that you want to identify as you are writing your code. The next thing you want to do now, so if you can write, so let's say that you figured out, okay, I can write 512 bytes starting at here all the way over here. I can write it. I've established that, no problem. So what else is left now then for me to cause serious damage on this system? So what else do you want to do? So you can write 512 bytes into the stack, right? You know the CPU will, oh, I'm pointing to the wrong place here. You guys didn't tell me. Return address there. The CPU will execute that return address. So you know you can write there. What's your target? Of those 512 bytes, what's your main target, do you think?
Would it be the bytes that overlap the return address?
Yes, very good answer. This is your main target. Very good. That's your return address because, so now what does that tell you? It tells you that, let's say that this is 12 bytes and let's just say this is 12 bytes or for whatever reason, that's 24 bytes, right? So your address should be at 24 bytes from the beginning. So let's say that 24 bytes is, I'm going to use another color. 24 bytes is basically that. So that means that your address should be there. Do you see that? That should be your address right there. So you just figured out, instead of writing, this is a very, very, very long string, right? This is a very, and then in that particular segment, right, where the address might be 2 bytes, you put your address there. So now, let's say that instead of having, this is a very, very, very long message, you now have in there, oh, you have, no. I wish this had an undo. Well, that's going to be it. Right, so that's, I think it was like that. All right, and so in there, you want to write your address. You see that? So that you can overwrite it. So for instance, I'm just going to, you want to overwrite this address with some other address. So you just need to figure out the positioning. So let's say 24 bytes in, start writing the address. Now this is a very important concept, right? Because you will have to do this. You'll have to figure out where to place your address in the string. This is the code injection, if you think about it. The code injection is nothing more than when the program is executing, is going to give you an opportunity to write something. So in this case, you're going to write this. That's your input, the user provided input. But you figure out that somewhere around here, you will place the address because that's where it will coincide with this segment over here, and you can overwrite the return address. Now that's another piece of the puzzle. What's the last piece of the puzzle? Because if you've understood all of this and then you understand this last piece of the puzzle, you've got the big picture, and then all you have left is really the details, right? So what is the last piece of the puzzle, would you say?
You have
You know how to write it. You know how it's vulnerable. You know that you need to align the address to the return address. You know that the CPU will eventually execute that return address. So the question is, what's the last piece of the puzzle?
Do you have to be able to write the other address and another space?
You
That address to,
so are you saying what address? You're right here. Is that what you mean?
Mhm.
Yeah.
right up there, yeah.
Exactly. So you know that you can write an address, but which one? Do you see that? That's the last piece. What address do you write? Because remember that you don't really have access to the code, right? So you can't just write a shell script, you know, so you need to figure out what address to write in there. It's that simple. Make sense? So this is going to be a to be continued movie. All right, so we're at the end of class right now. So in the next, you know, this is to be continued, right? Dot, dot, dot. So in the next lecture, we will pick up here. This is a very good, please remind me if I ask you guys in class, this will be where we're gonna pick this up now. So you figured out all the structure, you know how to put in the input, you know that it needs to be aligned. So what address do you insert in there? There are thousands of possibilities, right? So you need to figure out. So that will, you know, we'll pick up there. Okay, so in the next lecture, we will talk about which or what address. All right, and that concludes today's lecture. Hopefully it made sense to you guys. Definitely read the book, you know, start reading at the chapter. Have questions next time. And next time we meet, we will go over the labs as well. All right. All right. So I'll stay for a couple of minutes for those of you that have questions. Otherwise, I will see you guys Thursday.